If you've ever managed a server or even just used Get, you've probably typed SSH 1,000 times. And it just works. It feels like magic, right? You type one little command and bam, you're controlling a computer that could be thousands of miles away. But what is actually happening in those few seconds before you get that command prompt? Well, it's this incredibly complex and really elegant dance of cryptography. So let's dive in and take a look at this invisible handshake that secures a huge, huge part of the internet.
So to pull back the curtain on SSH, here's our game plan. We're going to start with the basic problem it was designed to solve. Then we'll walk through the whole connection process, from that first digital handshake to building the secure tunnel, the final ID check, and finally, we'll see how this whole incredible dance happens in the blink of an eye. Okay, so let's start at the very beginning. What is the fundamental problem we're even trying to solve here? Well, we have all these servers scattered across the globe, right? And they need constant attention. We're talking updates, file transfers, you name it. The real challenge is, how do you do all of that from your desk without your commands and, more importantly, your passwords being broadcast for literally anyone to see and intercept? I mean, that's the core question, isn't it? Sending your commands over the open internet is kind of like shouting your deepest secrets in a packed football stadium. Anyone could be listening in. Or, even worse, someone could pretend to be your server to try and steal your information. We absolutely need a private, secure line. And that's exactly where SSH, or Secure Shell, comes into the picture. It's the protocol that was designed specifically for this job. It creates this private, encrypted tunnel right through that crowded public stadium, making sure that only you and the server can understand the conversation. All right, so the whole process kicks off with what we can call a digital handshake. Before any of the really heavy-duty encryption starts, the client, that's your computer, and the server first need to make contact and agree on the basic rules of the road. First up, your computer starts a totally standard TCP handshake. You can think of it as the internet's basic way of saying, "Hello, you there? Yep, I hear you. Okay, great, we have a connection." As soon as that line is open, they immediately trade SSH version numbers. If they're both using a compatible version, like SSH 2.0, we're good to go. But if they're not, the connection drops. Instantly. There are no compromises. Okay, now we get to the heart of it, the really cool part. With that basic contact established, it's time to build that secure encrypted tunnel. And this is so important. This happens before any sensitive information, like your password, is ever sent across the wire. This whole thing happens in 4 key stages. First, they need to agree on what encryption algorithm they're going to use. Second, your client has to verify the server's identity. Third, they generate a shared secret key. And finally, they create the actual session keys they'll use for the conversation. Let's break down how each of these pieces locks into place. So, authenticating the server is absolutely crucial. Your computer needs to know for sure that it's talking to the real server and not some imposter. So the server sends over its public key. Your client then checks this key against a little file on your computer called known hosts. If it's the first time you've ever connected, it'll ask you to confirm. But if that key has changed since the last time you connected, SSH will scream at you with a big warning because that could be a sign of a man-in-the-middle attack. Now for the part that honestly feels like a magic trick. Creating a shared secret key right out in the open. Using an algorithm like Diffie-Hellman, they do something that just seems impossible. Imagine you and the server each have a secret color of paint. You publicly agree on a common color, say yellow. You each mix the yellow with your own secret color and send those mixed results to each other over the network. Now, anyone can see these mixed colors, but then, and here's the magic, you each mix the color you just received with your own original secret color, and in the end, you both magically arrive at the exact same final secret color without ever having sent it directly. That shared color, that's the secret key. And from that one single shared secret, they generate a whole set of keys just for this one session. There are 2 keys for encryption, one for data going to the server and one for data coming back. And then there are 2 keys for integrity. These are often called MAC keys, and they act like a digital fingerprint on every single message to make sure nothing was tampered with along the way. Okay, the tunnel is built. It's private, it's encrypted, and its integrity is guaranteed. It's only now that the server asks the big question. All right, I know this line is secure, but who are you? It's time for you, the client, to prove your identity. And you've really got 2 main options here. You can use a password, which is simple and easy, but it's also pretty vulnerable to brute force attacks. Or you can use the much more secure method, public key authentication. Yeah, it requires a little bit of setup up front, but it is vastly superior from a security perspective. Public key authentication works with this really clever system. It's a kind of challenge and response. See, the server doesn't ask for your secret private key. That key should never, ever leave your machine. Instead, it comes up with a test that only someone who has that private key could possibly pass. And this is how that brilliant little flow works. The server sends you a random message, just some gibberish. Your client then uses its private key to create a unique digital signature for that specific message. It sends just the signature back. The server then uses your public key, which it already knows about, to check if that signature is valid for the original message it sent. If it checks out, that proves you have the private key, and boom, you're in. So let's just recap for a second. All of this, the handshake, the version checks, negotiating the algorithm, authenticating the server, generating 4 different keys from a shared secret, and then the client's final ID check, all of that happens in the blink of an eye. Looking at this timeline, you can really see the logical progression. We start with a totally basic, insecure connection. And then step by step, we build these layers of trust and encryption on top of each other until we finally have a fully secure session, ready for your commands. And the result is just so powerful. We have a communication channel where absolutely everything is encrypted. Both parties have proven who they are, and you can be 100% certain that the commands you send are the exact commands the server receives. It's really the bedrock of modern server administration. All of that complexity, that entire cryptographic ballet, happens behind a single command you type. It kind of makes you wonder, doesn't it? What other invisible systems are working silently in the background of our digital lives, protecting us every single day, just waiting to be explained?